Okay, I think we can start today's session, guys. So this is going to be the last topic in the ROS 1 course. Okay, and the topic is state machines. Okay, state machines. So um, I actually work with state machine, but not much. So I actually need some time to study these things. So that's why it's took actually some time to take this topic to discuss. So as of now, I have read something. I know there are libraries existing in ROS to work with state machine. But before that, I just want to give you the basic idea, like why we have to use state machine, or what is state machine, and what is the use of state machine in robotics. That is the important part. And how can we implement state machine using ROS or Python. Okay, so this is what the objective of this chapter. Okay. So maybe first we can start with an example. Okay, with an example. Fine. So let me do one thing. I'm planning to start a simulation. Okay, I'm just planning to start a simulation. Turtleboard. Okay, turtleboard simulation. Give me some time. So I'm just taking the navigation. Need to change some parameter there. I think the base local planner, because no, just want to run this simulation, guys. So before that, need to change some parameters. Or maybe I can directly go to that folder. Turtle about 3. What was that path? SRC turtleboard 3. Okay, and navigation, and this is where the parameters. So maybe we can check whether the parameters are here, or okay, it may be in the launch file itself. So just taking the move base, yeah, this is where it is. So I actually changed the global planner of the navigation stack to a new planner for testing. Like while we were discussing the there is a chapter actually like discussing how to create a global planner. We already discussed that. So I actually changed this parameter. Like this is a custom global planner that we have seen in that chapter. And there were some issues with this planner, so I'm just using some some default planner. I think this is also will not work. I think yeah, this is fine. This is fine, I guess. So let me start a simulation. Okay, so then only I can explain the context. Just a second. Okay. So I'm starting the turtleboard simulation world. I think you all are familiar with this. Okay, so here is the simulation we have, and now I'm starting the navigation. So launch turtleboard 3 navigation. Okay, I'm starting it. Okay, you can see the map, right? Yeah. So it is working, and let me give a goal position, and you can see it is moving, right? Okay, so imagine this world as a cafeteria, cafe. Okay, and imagine these objects as tables. Okay, so in cafeteria what is happening is that there will be a kitchen and there will be table, and you can order the food. Okay, so in some cafeteria they offers a tablet to place the order. In some cafeteria a waiter will come and give the menu, right? And it will be taking the orders and it will be giving to the kitchen, and then whenever it is ready it will be delivered, right? So if you want to do this operation, or if you want to automate this operation using a robot, okay, that is quite possible, right? I mean, this is a scenario, like you can see, is very similar to a cafeteria, and if a robot want to deliver food, in case, you can just give a command. Oh, sorry. Just a second. I think I have given a wrong. Okay, just want to correct it. Okay, fine, I guess. So you can give the goal position, and then the robot will be like coming near to the table, maybe for taking the orders. Okay, it may have some tablet and you can order, or maybe it may be delivering food. Okay, so if you are trying to create some kind of automation, okay, in any robot, so this is an example, like a waitress, waiter robot, or a food delivery robot. In all this scenario, there are some interaction happening with user. There are different states actually happening. For example, whenever the food is ready, the robot will be delivering the food near to the table. Okay, and whenever the food, I mean the food is over, maybe the robot will come and maybe you can put the plates on the table, on the top of the robot, and the robot will be moving that plates to the kitchen or something. Okay, so if we want to create some application like this, okay, how can we create like this application is having set of states, right? Like going to the kitchen, if the food is ready, then take the food from kitchen to the table, and if so, like there are a lot of conditions, right? There are a lot of conditions. So if we want to work with this kind of application, okay, which is having different conditions and different states. Okay, state means like it is going from one state to another. Like whenever the food is ready, then it will be doing something like that. Okay, so in order to do implement this kind of application, one of the method, okay, one of the I will say one of the first method. Okay, there are better methods compared to this. So one of the method that we can use is FSM, finite state machine, or like simply state machine. So a state machine is kind of simple algorithm, okay, in which we can actually sequence the complete operation. Okay, complete operation that we can easily sequence. Sequence means like when the robot start, what is the first thing it has to do? Okay, and after doing that, what are the outcomes and what is next? So we are simply sequencing the entire operations of the robot from the start to the end. Okay, so simply if you want to control the robot in this kind of environment, you can program like using if else loop. We can program like if the robot is here, do this. If the robot is here, do this. We can simply create application like that. But there are some standard methods, standard techniques available for creating this kind of application. Okay, so if you take any robotic application, it may need some kind of commanding or some kind of what will I say, like task structuring. Okay, so for example, if you're working with a drone, there will be an application tied up to it, right? Like it may be like flying and doing some mapping, and maybe it may be finding some intruders, and then it will be reporting. Okay, so there will be lot of states in a particular robotic application. So that's where the ROS actually come into the picture. To implement this kind of application, ROS offers different libraries to ease the entire operation. Okay, so one of the main library is the action lib. Okay, action lib. So I'm not sure you work with action lib thing. Action lib, I think you already know about it because I already discussed about action lib in the first chapters. So action lib is simply, I can demonstrate again with the simulation and navigation. I can show you what is action lib. So you already know what is a topic, right? ROS topic. So ROS topic is actually like sending the message continuously. There is no feedback in the sense there is no acknowledgement sending from the sender to the receiver or receiver to the sender. It is continuously sending, kind of asynchronous. It's continuously sending and the receiver is receiving it. But in case of ROS service, so what is happening in ROS service? In ROS service, it's like a request response. For example, there is a ROS server and ROS client. So client will be requesting to the server. Okay, and when the server get the request, it will be checking the request, and it will be doing that request. It will be like executing that request and then send back with some acknowledgement, like it has done this job or not, something like that. But what about action lib? That is the next level of communication in ROS. Okay, communication pattern. For example, I am giving a goal position here. Okay, and robot is trying to achieve that position, right? Before achieving, I am giving another position. Okay, and before achieving that, I am giving another position. So what is the behavior that you are seeing? Like whenever you are giving the position, it actually cancels the current operation. Okay, like it is cancelling. Okay, and it is taking the new job. Okay, so in case of ROS service, is this cancelling possible? No, right? Like when you give a request to the robot, it should complete the task. Then only we can give you a new goal. Okay, but here the ROS navigation stack is actually using action lib. Okay, action lib is simply, it's actually the concept is, it's very simple concept, but implementation is somewhat difficult. Action lib is that we can give a goal to the action lib. Okay, and the node, again we can say there is an action server and action client. Okay, so action client is sending a request to the action server. Okay, and the action server will be receiving the request and it will be executing that request. Okay, and imagine if this request need 10 minutes to complete. Okay, we are giving a request, like we are giving a navigation, and imagine the robot takes too much time to complete. Okay, so we are thinking, oh, robot is taking too much time, so let's cancel this operation and give a new goal. Okay, so using action lib, we can able to do, or we can implement those kind of application. Meaning we can give a request, and whenever we are not interested in that request to continue, we can cancel it or preempt it. Okay, and then we can give a new goal position or new goal position. So what you are seeing is an implementation of ROS action lib. Okay, the ROS move it is ROS navigation stack, even move it also using action lib library. Okay, it's not, I can't say it's a library, it's a communication, a type of communication, and we can able to give a goal position and robot is trying to achieve, and if you give another goal position, it is cancelling immediately and it is reaching the other goal position. Okay, so why I am talking about this action lib is that we may need this action lib for implementing many applications. Okay, because in real application, we may be like giving some task to the robot, and the robot may not get while doing that task, the robot may not able to complete that task, okay, within a certain time. So we can say, like, we can write a program in a such a way that do this task for like 3 minutes. Okay, if it is not completing within 3 minutes, just cancel it and do this. Okay, so this is what we are mainly implementing using state machines. Okay, so the state machines are like a what will I say, a structured list of tasks. Okay, structured list of tasks that to be executed with respect to each condition. Okay, with respect to each condition. Yeah, that is actually the state machine. So I just want to give a reference first. That is one of my book actually. That is actually authored by, this chapter is authored by Ram Kumar. So I can show you a chapter which is having the importance of state machine, importance of action lib. Okay, and he's also mentioning about some examples as well. Okay, so I am actually using this chapter to discuss today's topic. Okay, and so we have seen what is an action lib and the importance of action lib, and then we are starting with the state machine concept. Okay, because in the backend we need the action lib for working with the state machine. Okay, so let's start with the state machine concept. So let me open it in the PDF viewer. Just a second. Okay. Fine. So here, where is it? Yeah, this is a chapter. Okay, handling complex robot tasks using state machine. This is the 4th chapter of the book, ROS Robotics Project, 2nd edition. I can share it. Okay, so first we have discussed about the action lib. So action server and action client. So this is what I mentioned. The action server is actually executing the task. Action client is what requesting the task. Okay, so so it is giving a goal to the action server, and then the server will be giving some feedback. Okay, so I discuss about the cancelling of the goal, but I didn't mention about the feedback. That is also a very important part of the action lib. Okay, so whenever you give a task request to the action server, okay, goal request to the action server, it will be continuously giving the feedback. That is an important stuff, because we actually instructed the robot to go to XY 1010. Okay, and when you give the goal position, the robot start moving. Okay, the robot start moving. And if you are not getting any kind of feedback, then we don't know where the robot is. Okay, but using action client, action server, we can implement this feedback. So if the robot moves 1 1, okay, or 1 0, the action client will always get the updates. Okay, so the action client will have all the updates about the robot. That is one of the important part of the action lib. Okay, so we can cancel the request, we will get the feedback, and also after completing the task we will get a final result. Okay, so these are the importance part of the action server, action client. And why I discuss this topic, because this is the backend of most of the state machine libraries. Okay, so the state machine library is actually using ActionLib as the backend. Okay, so simply the state machine I mentioned, like it is like a sequence of some state going from one state to another. And for example, if the robot is not completing its task within a certain time, it has to cancel it and go to another. So in that kind of situation, this ActionLib is the basic foundation for the state machine library. Okay, so for showing an example with the state machine, he actually discuss an example with a gazebo simulation, and he also created a sample action server, action client code. So you will get an idea like how the action server and client looks like. I think we already seen that in the first chapter. Okay, there are sample codes already there for the action client, action server. And after this, he's starting with a the importance of the state machine, or like why we need a technique to sequence a list of jobs. Okay, not only sequencing but also controlling the flow of the sequence of the task. Okay, so that's where these examples comes in, the cafe example. So here is a robot. You can see it's a robot home, and there is a delivery area, there is a kitchen, and these are the tables. Okay, so using this scenario, we can easily explain, or we can explain the state machine concept in a better way. Okay, so that's why he mentioned this example. Okay, so before going to advanced state machine stuff, I think we can start with some basic stuff. So this is what I mentioned about the state machine, so you can easily understand with a picture. So here this example is for the cafe. Okay, so there is a button in the customer table. Okay, so whenever it is high, okay, it means they ordered a food. Okay, they ordered something. So if it is high, it is success, and it is going to another level or another state, which is order confirmation. Okay, so order confirmation, it is doing the order confirmation, and if the order confirmation is successful, then the order confirmation is successful, then what? It will be going to the delivery area. If it is failure, what is happening is it's going to the kitchen. Then from the kitchen, someone will come for speaking. Okay, what is the problem with the order confirmation? And then whenever it is successful, it will be going to the delivery area for taking the food. Okay, so Bharat is having a question. Do we have any tools for state machine design? Yeah, so Bharat, I am coming to that actually. Okay, so there are some tools. So just want to introduce this concept, those who are not aware of it. Okay, even I am not an expert in this, but just want to give a basic idea. Okay, so this is actually the state machine concept of the restaurant delivery robot. Okay, that we have seen. If you want to, I mean, if you want to represent the states of a cafe, these are the states. Okay, there is no robot included, but only the states of a cafe. Okay, and now we are coming to the main point. Okay, so you got a basic idea of the state machine, like one state to another, and if it is failure, doing something. Okay, so what is the advantage of like creating this kind of structured states in a robotic application? It's very easy to debug, right? It's very easy to debug. We are not hard coding anything. We are actually taking each instance or each input, and based on the input, do this. If the input is different, do this. So we are like orchestrating all the possible income or a possible task in the state machine, and then it's very easy to debug. Okay, so in order to create a state machine, there are some libraries available. Okay, we can create one state, and whenever it receive an input, then it will be processing it, and then it will give an outcome, something like that. So that is where one of the tool, that is where Smash coming in. Smash. Okay, it is actually stands for state machines itself. Okay, so just a second. So Bharat, at any given point of the time, we know what is the state.
I mean to say the advantage of state machine is basically we can control the logic, and we know the logic how it flows, and which state mainly the processing taking place.
Exactly. So
Because if else conditions will have a lot of sometimes we can screw up things.
yes.
Whereas state machine, we use the enums, and those state controls will only be done in that particular boundary.
Exactly. So just want to give a visual example. So I actually will discuss this after discussing Smash, but in order to give a feel of it, I think it's important to show this. Just a second. Let me. Okay. So I'm planning to show you like what is the advantage of using a state machine library. Okay, so you can see here, this is a visualization of the state machine that we have created. Okay, and you can see the green the states are actually going to green one by one, right? So what it means is that it's actually reached here. Okay, it's actually reached here. It's reaching one by one. Okay, I'm repeating it. Okay, so if you have this kind of visualization for your robotic application, okay, this is a very simple representation. Very simple state machine. But if you have a very complex list of tasks, okay, and if you use the state machine library for creating your robotic application, the main advantage I am seeing is it's very easy to debug, because we will get the visualization of the flow of the program. That is very important, right? Because I remember I have participated in one of the robotics challenge called HRATC, which is actually the task is mainly like autonomously finding the mines from some area. Okay, so at that time I didn't use the state machine. Okay, because I was not very aware of this. But some of the other teams, they actually implemented using state machine. Okay, and they got more marks. Okay, because the advantage is that we will get the exact point when it is failing, and what is the things that we need to change, and moreover it is very modular in design. Okay, very modular, so we can able to debug it very easily. Okay, and another thing is that this state machine called Smash, state machine library called Smash, it is a Python based library. Okay, again it is very easy to program. Okay, so these are the one of the library for working with the state machine is Smash. It's actually very very popular. Maybe I can show you. This is where like this is what we need to know, like if you want to implement state machine, what are the libraries that we have. So just want to share. Smash is actually not a ROS based library. It's an independent library. Okay, it's an independent library, but there is a ROS wrapper for it. Okay, so there is a video actually showing the implementation of Smash. I think it's a very old video, but you can able to see the demonstration of Smash. This is for a complex application. You can see it's a very big one. So here you can able to find, just a second. Okay, you can able to find navigate to fridge. Okay, so that is actually a task. Okay, that is actually a task, and that task will be triggering whenever it is getting some input. Okay, so whenever it gets some input from here, you can see here there whenever it gets some input, user input, it will be triggering the navigate to fridge. Okay, and whenever the navigation to fridge is completed, then it will be going to the next phase. Okay, so if you have like 10, 20, 30 set of tasks to finish, then you can imagine which way is better to create this kind of complex application. Okay, obviously state machines libraries actually giving the flexibility, okay, to create the complex task in a very in a good way, I will say. So here you can see so after one of the state task was open gripper, and if that is successful, then the next task is approach handle. Okay, if that is successful, move to grasp handle. Okay, so you can see it is completing each task. So we will get a clear picture of what is happening, because they are actually doing very very complex scenario. Like I think you have seen these demos, right? Like playing the pool, then taking beer from the fridge. All these things, all this application actually orchestrated using state machine. Okay, it's not like record and playback kind of thing. It is a structured organization of the task. Okay, and it's not like predefined kind of thing. Okay, all these things are autonomous. Okay, so in case of autonomous robot, these state machine implementation will give you flexibility to create better flexible debug, I mean the code that we can debug, it will give all these things. Okay, so like the concept they actually mentioned, the basic concept here. You can see what is states. Okay, so it's actually what the robot to exhibit as a behavior or simply execute an action. Okay, and so what we are seeing, the task that we have mentioned, this we can call it as a state. And what is the outcome here? If you see, navigate to outlet, and what is outcome? It is succeeded. Okay, that is outcome. And what is the input? The input is now plugin. That is a user input. So that is a state. And inside each state, when the robot, for example, when the robot comes to navigate to outlet state, it will be executing it. Okay, it will be executing it. And if it is succeeded, it will be going to detect outlet. If it is failed, then maybe it will be going to another state. Okay, so this kind of way, if you program, it's very easy to create the application. Okay, and containers, this is another terminology. It's a collection of states. So we can say this is a container. Okay, this is a container. So we can create many containers. Okay, so each blocks, we can say containers. So from one block, after completing one block or one container, we can actually like reroute to another block. Okay, so state machines using Smash will give you flexibility, but in order to work with it, or in order to learn it, rather than just going through the tutorial, you have to create application. This is very important, because then only you will get the actual feel of it. Okay, I actually create only very basic things. Like if you create or orchestrate all these kind of connections, I mean, then only you will understand the importance of it. Okay, so states, then containers, and outcomes. Outcomes are the output from each state. User data is the input. Okay, preemption, I just mentioned about the preemption. Preemptions are just like canceling. Okay, so if you want to interrupt a state, that is called the preemption or canceling. Okay, introspection means, I think we have seen the visualization of the state machine, right? That is called the introspection. Okay, so these are some terminologies, and you can see here an explanation. So the green arrow green block indicate active state. Then the connection from one state to another called outcome. Okay, and on the right side you can see user data. Okay, user data simply the input. Okay, so what is the input from one state to another, you can see here. Yeah, so now it's a time to get started with the Smash in ROS. So there are good amount of tutorials available in the ROS wiki. Okay, maybe I can actually share it. And in order to install, again, it is very easy. So the command is already given here. Or what you can do is, what I have done was, I used this command. Instead of Smash ROS, I install all the package of Smash. Like you can use like this. Smash star. Okay, so it will be like installing all the packages starting with ROS Smash. Okay, so so that's how we can install Smash on your computer. Okay, so there is a command here on the book. You can find all the packages, but it actually mentioned about melodic, but the package name is the same. Okay, instead of melodic you can use the noetic. Okay, yes. So there is another example, like if A is 1, then go to B. If A is 0, go to D. If A is 0, go to C. So it's like transitioning one state to another. That is what it is showing. Now I can show you the first example that we are currently playing in the background. You can see here, this is the first example that we are going to see. Okay, so what is happening here that we are going to check. After that, I think we can conclude today's session. Okay, so let me show you the first or hello world program for the state machine. Okay, for the first time it actually looks complicated to me, but now it is better. Okay, yeah, so maybe I can go through this code, so you will get some idea. Okay, fine. So this is the Python code. This is the ROS Python node. So what is happening is, we are initializing a node that I don't know you work with ROS Python. Mostly we have been working with ROS CPP, but this is how in ROS Python or ROS Py we are initializing a node, and this is a class that we are using for state machine. Okay, so if you just go on the top, you can find the important modules that we require to work with state machine. So first is obviously ROS Py. ROS Py is the module that that we are using for working with ROS and Python. Okay, this is the important module. Okay, ROS Py, like the ROS CPP.h, or we are using ROS.h, right, in the CPP code. So like that, for Python it's ROS Py, and this is the class that we require. Okay, I already mentioned that it's a Python library. So inside this library there is two class mainly that we need. One is state. Okay, state class, it's a class, so that represent a state. Okay, and state machine, it actually the complete, it is having all the state. Okay, so state represent the individual state, and state machine is having multiple states. Okay, and we are also importing smash ROS, which is the module which is interfacing to ROS, I mean smash and ROS. Okay, so if you see here, we can see there are 4 classes. Okay, 4 classes: class A, class B, class C, and class D. Okay, and you can see on class A, class B, and class C, D, this is what we are doing inheriting. Okay, inheritance, you heard about inheritance, right? So in Python, in a class, we can do the inheritance using this. Okay, so class A basically initialized with a state. So class A basically a state. Okay, it's a state. Class B is a state, class C, D, everything is a state. So how much states that we have? 4 state. Okay, so inside the state we can define input, output. Okay, and the execute loop. Okay, so just think, like for a state, it actually need a trigger input, then only it will be triggering. Okay, so whenever it get an appropriate input from other state or from user or anything, it will be execute this function. Okay, after executing this function, it will return an outcome. Okay, that is the outcome it is showing here. Okay, so this is what we are initializing the class with the state, and you can see these four states are the same only. Okay, it's actually same only, different class name, that's it, that is the difference, but it is the exact replica. Okay, so this is how we are writing a state. Okay, execute is what executing when it get an input. Okay, when it get an input. So we define the states, and now we have to create the state machine. Okay, so that is what showing here. Okay, state machine is the class, and outcome equal to success, that I will get back. So here we are creating a state machine. Okay, state machine object called SM. Okay, and for this state machine we can set a user input called 1. Okay, so inside the state machine we can set the user input to 1. Okay, and so we defined a user input for the state machine. Okay, and then we are adding these states to the state machine. So state machine add A, state machine add B, state machine dot add C, state machine dot add D. Okay, and then giving the transitions, remapping, all these things. So I will be explaining that. So transition basically like if it is 1 going to B, if it is 0 going to D. For state B, if it is 1 then going to C, if it is 0 going to A. Okay, maybe I can run it again so you will get a clarity. Just a second. You can see here. So just take A. Okay, just take A. So what is the transition state transition that we are seeing? If the input is 1, okay, if the input is 1, okay, for the state A, what is the next state it will be transitioning? It will be transitioning to B, right? It will be transitioning to B. B means the class, this is the state machine name, this is a state machine class. Okay, so basically we already give the input as 1. So the first state machine in the first state is A, okay, that we have added. So whenever it receives 1, it will be going to B. So that is what it is showing. Okay, A to B. And when we reach B, there is again outcome from B. You can see here. So for B, if it is 0, it's going to A again. If it is 1, then it will be going to C. Okay, so whenever it's executing the B, the user input is actually 1 again. Okay, so you can find in each state we are giving the user input, like if the user input is 1, then it will be returning 1. Okay, so first it will reach A, and it already getting 1. Okay, user input we already set as 1. So what is the return? 1 will be returning. So 1 will be going to B. Then what will be returning? B will be returning again 1. Then it will be going to C. Then what will be returning? It will be going to C, D. Okay, so that is what we are seeing here. Like uh, is going to A, B, C, D, and again B, again A. Okay, so this is like a loop. Okay, so if I am just giving it 0 for, okay, I'm giving the first user input as 0, and let's see what is going on. See, you can find what is the transition value that we are seeing. If A is having 0, it will be jumping into D. Okay, and whenever it jumps to D, so it will be returning 0 again, so it will be going to C. So it will be going in a reverse direction. You can find A to D, C, B, A, D. Now it's in clockwise direction. Previously it was in anti-clockwise direction. Okay, so based on this input, we are changing the direction of the state. Okay, so that is how we are orchestrating the state machine. Okay, the approach is that write a program with ROS, then add the Smash library and the class, and then create your own state. Okay, so a state, this is a very simple state. In reality, a state class will have a lot of functions. Okay, and it may be doing some pick and place, or it may be detecting something. Okay, based on that, it will be returning an outcome, and we are defining the transition here. So based on the transition, it will be moving to one by one. Okay, so after creating the state, after adding the states, it is also starting introspection server. So if you define this, then only we can visualize the graph like this. Okay, and we are starting the introspection server, and then we are executing the state machine. So that is what happening here. Okay, so this is the very simple state machine, like a hello world state machine. Okay, so I just want to like ask you, like, if you did you understand the concept, or like if you have doubts, let me know. Like, did you got that idea, like how the state machine work, how the procedure, like creating state, adding to state machine, then defining the transition, and then introspecting using the Smash viewer. Okay, so based on this, we can we can see what is going on. Okay, so let me know if you have any question. This is the topic that we are going to discuss today. Tomorrow we will be, yeah, Bharat.
Yeah, I
Yeah.
have a sense. As I said, do we have any UML kind of tools where it generates a code based on the design of these states? Like we have a lot of things like tools in UML, Artisan, or some different tools are there in the market. I was using in my career, so I'm just asking whether in ROS it is there
You
or not.
mean like saving this? It was not clear. Like for the state.
I mean to say, like I instead of doing a code myself, I only design the states here, how it is
Okay.
showing here. So based on that, it will generate the code.
Yeah,
It is
yeah,
something
yeah,
like
yeah.
a
I got it.
UML,
I got it. I got your point.
UML
Yeah.
thing.
So there is a thing. So that is actually the FlexB. Okay. Called FlexB, and in SMAC also I think we can do visual programming. Visual programming is what the word is. FlexB is not actively supporting, so I'm thinking of whether we need to discuss it or something. This is like a visual kind of programming, so that using a GUI, we can create the state, and inside that we can code, and it will be auto generating the code. Okay, so I have used,
Yeah, that is
yeah,
what I actually mean, because as we do more complex, only state machine will be used in a more complex logics
yeah,
where
yeah,
it involves, and it definitely take this type of tools will basically it benefits the user programmer
yeah.
to
Yeah,
generate the
but
code.
these using this code, it's actually auto generating. um, but if you understand to create the basic state, and how to add it, then it's actually easy. Like, but again, what you said was correct only. Like, if when we approach to a very complex scenario, then I think a UI will help. So that's what the FlexB behavior engine, it will be helping. Uh, I don't know like whether it is actively supporting. Um this is having a UI in which you can uh, add blocks, and also like you can decide what is the input and output, and when you double click now, you can able to see the state in a Python format, so you can modify it. Anyway, I think we need to modify the code at some point of time, because using the behavior engine, we will only get that flow, like mainly get the transition, like one state will be going to another state, but we need to fill inside, like what is this state doing. For example, in case of, yeah,
And logic of inside the B state, what
exactly,
exactly you
exactly,
wanted to call the different
yeah,
APIs, or
yeah, yeah.
what are the things you have
You
to do
have
here.
to
That's it.
write the execute statement. For example, if the task is detecting an object, that detection code should be inside this class. Okay, and then if it is getting the outcome, it will be returning it. So that is our duty. But it will be giving this GUI based programming will give you a flexibility to create a very complex, because this FlexB, no, the FlexB actually created for the DARPA challenge. I think WPI, they actually mentioned for the humanoid challenge, I guess. So for maybe I can simply show you. Robot. So this is the main DARPA challenge. Yeah, this is a main application. They actually designed it for this challenge, DARPA challenge. Okay. Yeah, I think this video. So I'm not sure you heard about the DARPA challenge, which is a very famous challenge, robotics challenge, and the prize money is worth 2 million or something. So this tool called FlexB is actually designed by this team for participating the DARPA challenge. So all these tasks actually executing by the state machine. So you can imagine the complexity of this. So like there are tons of tasks running on this robot, right? Like there are two arms, two legs, the balancing, perception, all these things are like running. So so that much complex the system is. So we need a sophisticated method to create robotic application for this kind of robots. You can find here. This is the level of application that we are doing with the robots that need some advanced techniques to orchestrate the task. So this is a very complex challenge, guys. Like the state of the humanoid robot, right? Especially with all these payloads, the robot will be very slow, and the task that it is doing is very complex, like opening this is a visualization from the robot, like it's taking steps, everything. I think most of the tasks are done using ROS only. You can see, yeah, I think these all are like created using RVs. So I think you got my point. Yeah. So that's it. If you have any doubts, let me know. So tomorrow or day after that, I will be discussing the last uh, code. There are some problem with the code for the restaurant robot. So we can see what is happening with the restaurant robot state machine. So it's like an application. Okay, so we can see how it is going. Okay, guys, so I'm concluding today's topic. Thanks for attending. So I will be uploading the video maybe tomorrow or day after that. Okay, so see you tomorrow, guys. Yeah.
So we can get your this chat
Yeah, I will be
group.
uploading it. I think I have shared something, but I will be sharing it. Okay. Okay.
Okay, thanks.
So that's it, guys. Thanks for attending. See you tomorrow or day after that. Bye, everyone.